At 3 a.m. in the command center of the Canadian Hazards Information Service in Ottawa, a seismic trace off Vancouver Island logged something impossible. Across a 120-kilometer line parallel to the west coast, 14 monitoring stations recorded identical high-frequency pulses within 4 seconds of each other. None registered a primary body wave because there was no sudden rupture along the fault, no main shock. What ocean bottom seismometers on the Cascadia subduction zone recorded was a coast-wide burst of episodic tremor and slip, a silent tectonic shift 30 kilometers beneath the seabed. Simultaneously, 3,000 kilometers to the east, Great Lakes monitoring stations under the International Joint Commission logged a surface elevation drop on Lake Huron that bypasses every seasonal model from the last 50 years. 3 distinct anomalies across a continent, resolving into one physical reality. North America's moisture and stress regimes are shifting at a velocity with no modern analog. Headlines called it a sudden heat snap or an unusual dry spell. That is a dangerous misframing. What is happening across these systems is not a temporary fluctuation or isolated weather bad luck, but a structural transformation in the continental moisture and stress regime. The accurate version is far more urgent than a bad drought headline. For the first time, paleoclimate reconstructions and real-time geodetic monitoring have put a precise number on this shift across a 2,000-year observational window. To understand why this is happening right now, you have to look at the physical mechanism driving it. Moisture stability across North America relies on a delicate balance between Atlantic moisture delivery, Arctic air mass penetration, and the jet stream position. When rising temperatures drive extreme atmospheric evaporative demand, soil moisture deficits compound. A deficit in spring means the ground cannot cool the lower atmosphere through evapotranspiration in July. That heat creates a persistent high-pressure ridge, deflecting storm tracks that usually replenish the water table. Think of it like an overdrawn bank account with escalating fees. If a system receives 10% less winter precipitation, but experiences a 25% increase in summer evaporative demand, the net loss compounds exponentially because the underlying reservoir never resets. When this dynamic repeats across 3 consecutive years, surface water reserves drop below intake elevations, groundwater tables collapse, and the missing water volume alters the crustal stress balance on regional fault networks. That physical mechanism is why this trend accelerates rather than self-corrects. By the time this episode concludes, we will answer one central question. Is this continuous continental drying a temporary overshoot that will stabilize, or are we witnessing the permanent relocation of North America's semi-arid baseline northward into the Canadian heartland? To place this shift in context, paleoclimatologists reconstruct past environments using physical proxies, from lake sediment cores in the Canadian Shield to speleothems in subterranean cave systems and ancient Douglas fir tree ring chronologies in British Columbia. These proxies provide a continuous, high-resolution record of precipitation, temperature, and evaporative stress extending back 2 millennia. Across that baseline, the data reveals periods of natural variability, the Roman climate optimum, the medieval climate anomaly, and the Little Ice Age all brought distinct wet and dry phases. However, the current rate of moisture depletion sits entirely outside that 2,000-year envelope. The drying rate is statistically distinguishable from any natural cycle preserved in the sediment and tree ring record. The atmospheric forcing, specifically the poleward displacement of storm tracks combined with thermal forcing, is actively altering agricultural productivity, municipal water security, and ecosystem stability across the continent. From agricultural belts in the Canadian prairies dependent on the South Saskatchewan River to critical transport corridors along major waterways, physical impacts are compounding. When soil moisture drops below critical thresholds across multiple seasons, the landscape loses its ability to absorb even normal rainfall, escalating flash flood risks while failing to recharge deep aquifers. Until we monitor 3 specific variables over the coming months, the situation remains a continuous trajectory. First, watch winter snowpack accumulation at the Columbia Icefield and Upper Athabasca Basin. If recovery remains 20% below the 30-year average, the compounding deficit cannot reset. Second, monitor whether Natural Resources Canada records an expansion of episodic tremor events migrating inland toward the Leech River Fault near Victoria. Third, watch for formal water allocation advisories issued by provincial authorities along major river basins. Until one of those markers breaks the pattern, this structural shift in our climate and geophysical system will continue to accelerate. A single notched wooden gauging marker on the shore of Lake Diefenbaker, driven into the clay near Gardner Dam in 1967, tells the story of North America's hydroclimatic design baseline. For nearly 6 decades, water resource management across the Canadian prairies and transboundary basins, resting between Canada and the United States, relied on one assumption: that the climate system would always fluctuate within a predictable, bounded envelope established during the mid-20th century. Civil engineers, agricultural planners, and municipal authorities designed massive storage networks, power grids, and water agreements around specific historical averages, measuring success against drought cycles like the 1930s Dust Bowl or the 1988 dry spell. Popular commentators still describe our current water and agricultural challenges as a simple recurrence of those historical drought cycles. That is a misinterpretation. What headlines loosely label as another dry spell is actually the complete breakdown of the baseline assumptions that built modern North America. The accurate story is not that we are experiencing a temporary swing in a natural cycle, but that the entire paleoclimate baseline, sustaining human settlement and agriculture across this continent for 2 millennia, has shifted. To see how far we have drifted outside the historic baseline, examine how paleoclimatologists and geologists map past climate regimes. Scientists at the Geological Survey of Canada and research institutions across North America rely on physical proxies preserved in lake sediments, ancient speleothems in cave systems, and tree ring chronologies extending back 2,000 years. By extracting core samples from deep northern lake bottoms and analyzing the geochemical composition of growth rings in ancient trees, paleoclimatologists reconstruct a year-by-year record of temperature, precipitation, and soil moisture. This reconstruction reveals a clear record of climate variability across the continent. During the Roman climate optimum, roughly 2,000 years ago, relative warmth and favorable moisture balances sustained dense agriculture worldwide. Centuries later, the late antique Little Ice Age of the 6th and 7th centuries brought cooler, wetter conditions, followed by the medieval climate anomaly between the 9th and 13th centuries, which triggered prolonged megadroughts across semi-arid regions of North America, destabilizing ancient indigenous settlements. Finally, the Little Ice Age from the 14th to 19th centuries produced complex regional shifts in temperature and rainfall. The physical mechanism governing these historical shifts was natural solar and volcanic variability, operating within a stable atmospheric chemistry background. When a multi-year drought occurred, it was driven by natural shifts in oceanic and atmospheric circulation patterns. When those circulation patterns eventually reset, precipitation returned, surface reservoirs recharged, and the moisture balance returned to its long-term average within a well-defined envelope of variability. That natural feedback loop no longer applies. Modern atmospheric forcing, driven by greenhouse gas accumulation, has fundamentally altered the physical baseline. Warming temperatures create a continuous background evaporative demand, operating regardless of seasonal rainfall variations. Even during years with near-normal precipitation, higher ambient temperatures cause soil moisture to evaporate faster than it can infiltrate into deep aquifers. When winter storm tracks shift northward, pushed by the expansion of the subtropical high-pressure belt, winter snowpack feeding major river systems like the South Saskatchewan, the Bow, and the Columbia shrinks dramatically. The compounding effect of elevated summer evaporation and reduced winter snow accumulation creates a permanent moisture deficit that an occasional wet season cannot clear. When you translate these physical metrics into scale, the departure from the historical baseline becomes stark. In agricultural regions that historically received reliable seasonal moisture, soil moisture deficits now match or exceed the worst years of the 1930s Dust Bowl. But unlike the 1930s, when cold winters provided seasonal relief and snowmelt recharged river systems, modern evaporative losses compound year after year across millions of square kilometers, an area larger than the province of Ontario. To track whether this structural departure from the historical baseline is accelerating further, watch 3 critical indicators in the coming months. First, monitor official streamflow gauges operated by the Water Survey of Canada along the South Saskatchewan River mainstem for late summer discharge rates dropping below historic minimum thresholds. Second, watch whether Environment and Climate Change Canada records an extension of autumn dry conditions past October across the agricultural interior. Third, check whether the International Joint Commission issues formal operational alerts regarding transboundary water allocations. Until those specific indicators show a return toward historical norms, the Paleoclimate baseline confirms that North America's hydrologic regime is operating far outside any natural cycle recorded in 2,000 years. A digital telemetry readout in the Dartmouth office of the Canadian Hurricane Center flickered at 14:22 UTC on a Tuesday afternoon, logging a sea surface pressure anomaly off the Atlantic coast that did not match a single operational forecast model. Within 45 minutes, 3 automated weather stations in southern Nova Scotia, 420 kilometers apart, recorded simultaneous dew point depressions exceeding 18 degrees Celsius in the middle of a high-humidity maritime airstream. These 3 readings were not equipment failures or separate local weather events. They were 3 distinct expressions of a single massive atmospheric engine breaking down. The seasonal shift between subtropical high pressure and subpolar low pressure across North America has reached a tipping point. Sensationalist news reports frame this breakdown as a sudden weather spike or an isolated climate freak event. That framing misses the point. What happened in that control room was not an isolated weather anomaly, but a sudden, observable shift in atmospheric circulation that paleoclimatologists have been tracking through long-term proxy data. We are watching the atmospheric feedback loop governing seasonal precipitation collapse into a self-reinforcing drying cycle in real time. To understand the physical mechanism driving this breakdown, examine how the atmospheric engine operates step by step. Under normal conditions, North American climate stability relies on a predictable seasonal dance. During summer months, subtropical high-pressure systems dominate southern latitudes, pushing storm tracks northward. In winter, as solar heating wanes, that subtropical high pressure contracts southward, allowing low-pressure storm systems from the North Pacific and Atlantic to sweep across the continent, delivering snowpack to mountain ranges like the Rockies and rain to regional river basins. That seasonal cycle has broken down because of 2 simultaneously acting mechanisms. First, greenhouse gas forcing has expanded the subtropical high-pressure belt northward, a process known as Hadley cell expansion. High pressure causes air to sink. As air descends, it warms and dries out, suppressing cloud formation and blocking storm systems from penetrating inland. High pressure that historically dominated regions only from June through September now holds its ground well into October and November. Second, dry ground reinforces the high pressure. When spring rainfall declines, soil moisture is depleted early. Normally, wet soil uses solar energy to evaporate moisture, cooling the surface and supplying local moisture for precipitation. But when soil is dry, solar energy directly heats the ground and overlying air. This sensible heat flux builds an intense dome of hot air that deflects Atlantic and Pacific storm tracks further northward. Storm tracks carrying winter precipitation are displaced poleward, preventing heavy snowfall needed to recharge river systems like the South Saskatchewan, the Bow, and the Columbia. The impact of this dual mechanism compounds year after year. A single dry winter leaves a deficit in soil moisture and groundwater. When the following summer dry season is extended by high-pressure blocking, evaporative demand skyrockets. When the next winter delivers below-average snow accumulation again, the system cannot reset. The deficit accumulates, creating a progressive depletion of surface reservoirs and groundwater that cannot be reversed by a single wet winter. Scientific evidence confirming this transformation comes directly from advanced monitoring networks across North America. Earth-observing satellites, combined with high-precision GRACE satellite gravity measurements, confirm that the physical mass of water stored in continental aquifers has dropped steadily over the last 2 decades. At the same time, automated streamflow stations of the Water Survey of Canada and soil moisture monitoring networks across the prairies document a continuous downward trend in deep-layer moisture that sits outside the normal envelope of variability. Convert this water loss into a physical scale you can picture. The total volume of moisture lost from regional water tables and reservoirs across the continent over the last decade equals more than 1,200 cubic kilometers of water. That is enough water to submerge the entire province of Nova Scotia under more than 20 meters of standing water, vanished through continuous evaporative demand. To track whether this atmospheric tipping point is escalating further, watch 3 specific indicators. First, check Environment and Climate Change Canada atmospheric circulation maps for high-pressure blocking ridges persisting over western and central regions past late October. Second, monitor whether Ocean Networks Canada detects sustained sea surface temperature anomalies off the Pacific coast that alter winter moisture transport. Third, check whether Public Safety Canada issues regional drought and water supply advisories covering multiple provinces simultaneously. Until those specific markers show a reversal, the atmospheric engine driving this continental drying will continue to intensify. On a blistering afternoon in late July, a digital water intake level display at a municipal water treatment plant along the Bow River in Calgary dropped to 1.8 meters, a critical operational threshold that triggered an automated alert-ready broadcast sent directly to hundreds of thousands of smartphones across southern Alberta. That vibrating emergency tone was not a drill or routine conservation reminder. It was the direct, real-world consequence of a continental moisture deficit cascading straight into municipal infrastructure. At that moment, river flow passing through the city dropped below 45 cubic meters per second, a rate historically associated only with late winter freeze-ups, not peak summer demand. Sensationalist news headlines framed that emergency alert as a temporary water management hiccup caused by a summer heat wave. That framing is misleading. What happened in Calgary was the physical breaking point where long-term regional moisture depletion intersected with urban infrastructure built for a climate baseline that no longer exists. Critical transport, agricultural, and power systems are experiencing systemic stress because the volume of water moving through our watersheds has dropped below operational minimums. To understand how this systemic stress plays out across daily life, look at the cascading physical mechanisms linking watershed depletion to national infrastructure. When snowpack accumulation at the Athabasca Glacier and Columbia Icefield contracts year after year, mountain headwaters lose their natural buffering capacity. In a normal climate regime, melting ice and alpine snowpack release cold, steady streams of water throughout July and August, maintaining prairie river levels long after spring rain ceases. When glacial runoff declines, river systems dry up, ground temperatures soar, and soil loses its physical coherence. This mechanism triggers a multi-sector domino effect. In agriculture, rain-fed cereal crop yields across the prairies plummet, forcing producers to draw heavily on groundwater aquifers that take centuries to recharge. As those aquifers drop, soil desiccation causes deep ground subsidence, fracturing subterranean pipeline networks and undermining highway foundations. Along critical mountain transport corridors like Highway 1 through the Fraser Canyon and major rail links feeding the Port of Vancouver, extreme ground drying followed by intense convective rainfall triggers massive slope instabilities and debris flows, severing national supply chains in minutes. The energy sector faces an equally severe operational bottleneck. Major hydroelectric utilities like BC Hydro and Manitoba Hydro rely on predictable reservoir elevations to drive turbines. When reservoir levels fall toward dead storage elevation, where water drops below intake penstocks, electricity generation drops off a cliff. Hydroelectric facilities are forced to curtail power exports, threatening regional grid stability during summer peak air conditioning demand. At the same time, northern supply routes relying on winter ice roads, such as the Tibet to Contoido corridor, see their operational season shortened by weeks, isolating northern communities and inflating the cost of essential goods. Translate the physical scale of this real-world impact into concrete numbers. Across the western provinces and northern territories, the total land area currently experiencing severe to extreme soil moisture deficits spans more than 1.5 million square kilometers. That is an impacted zone larger than the landmass of Quebec, affecting agricultural land that produces millions of tons of food annually and supplying water to over 7 million Canadians. To see whether this real-world escalation is heading toward an even more severe operational breakdown in the coming months, watch 3 checkable indicators. First, monitor whether BC Hydro or Manitoba Hydro issues formal operational notices regarding reservoir storage dropping below historical minimum intake elevations. Second, watch the Canadian Wildland Fire Information System for early season extreme fire danger ratings extending into northern boreal transit zones before June. Third, check whether the Canadian Ice Service reports a further reduction in winter ice road operating days along northern supply corridors. Until those markers show stabilization, the operational impacts of this continental drying trend will continue to escalate. On August 12, 2024, researchers from the Geological Survey of Canada stood on an exposed gravel bar along the Athabasca River near Jasper, measuring a surface streamflow rate that had dropped to 31.2 cubic meters per second. 6 days later, a rapid thermal anomaly across the surrounding watershed accelerated local forest desiccation, creating the exact fuel bed conditions that drove a high-intensity wildfire straight through the township. The scientists standing on that dry riverbed were looking at the precise physical intersection of hydrological depletion and sudden ecological failure, moments before the landscape transformed into an active disaster zone. Sensational headlines framed that event as an unpredictable, isolated natural catastrophe. That framing hides the real story. What occurred along the Athabasca was the direct physical outcome of a structural shift in our moisture regime that paleoclimatologists have now confirmed across a 2,000-year observational window. The accurate version of this story is that the underlying baseline of moisture availability across North America has broken away from its historical equilibrium, making events that once seemed extraordinary the new operational default. To understand why this shift is permanent rather than temporary, we must examine the physical mechanisms governing continental climate stability. The 2,000-year paleoclimate record synthesized from lake sediment cores, speleothems, and ancient tree ring chronologies proves that while natural moisture variability has always existed, from the Roman climate optimum through the medieval climate anomaly, the speed and scale of current atmospheric drying sits completely outside the natural envelope. The physical mechanism driving this shift is dual atmospheric forcing. Rising thermal energy expands the subtropical high-pressure belt northward, suppressing cloud formation and displacing winter storm tracks poleward. Simultaneously, severe soil moisture depletion eliminates evaporative cooling, building persistent high-pressure ridges that block incoming Pacific and Atlantic storm systems. This compounding atmospheric engine creates a vicious cycle. Lower winter snowpack across major alpine headwaters, from the Columbia Icefield to Rocky Mountain watersheds, means spring runoff finishes earlier. Elevated summer temperatures increase evaporative demand, stripping moisture from soils, deep aquifers, and surface reservoirs. Because the loss compounds year after year, a single wet winter can no longer restore the system to its historical average. What is definitively established by scientific consensus is that current moisture loss across semi-arid zones is statistically unprecedented over 2 millennia and is driven by forced greenhouse warming rather than a temporary natural cycle. What remains genuinely unresolved, the honest boundary of our scientific knowledge, is the exact atmospheric tipping point where this northern shift of semi-arid conditions becomes completely irreversible, and how rapidly regional microclimates will adapt to the new moisture baseline. To understand which direction this crisis takes from here, watch 3 specific checkable developments. First, monitor whether the Canadian Hazards Information Service and Natural Resources Canada report an increase in regional crustal strain readings near major fault zones like Cascadia, driven by the massive unloading of surface water weight. Second, watch whether Environment and Climate Change Canada confirms a 3rd consecutive year where the autumn atmospheric ridge persists past late October across western river basins. Third, check whether the International Joint Commission issues formal operational advisories declaring structural drought allocations along transboundary water systems like the Great Lakes and Milk River basins. Until one of those specific events occurs, the current situation is clear. North America is not experiencing a passing drought, but a permanent recalibration of its hydrological reality. We did not simply enter a dry spell. We crossed the threshold into a landscape operating on a completely different set of physical rules. Leave a comment below stating where in Canada or North America you are watching from and what local changes in river levels or seasonal rainfall you have observed over the past decade. If you want to stay ahead of the critical